So I'm Chandler Carruth. I work at Google on C++ and LLVM and compilers and performance and a bunch of other stuff. And I'm here to give a talk today because I feel bad, actually. I think I've been at CppCon in the past and I've talked about zero-cost abstractions. And I maybe even advocated that you all should use zero-cost abstractions. These are good things and that C++ is great because it gives them to us. But today I'm here to kind of apologize and say that I was wrong. A lot of other people were wrong. And in fact, there are no zero-cost abstractions. And imagining that there are is causing us serious problems. And so that's going to be the theme of this talk is, why do abstractions have cost? What problems does that cause for us? And how do we want to cope with that reality? So with that, let's start getting going here by thinking a little bit about what abstractions we really care about in C++. What do we mean when we talk about abstractions in C++ code? We'll start with the very simple, the very fundamental abstractions, the easy-to-use hammer that, doesn't take a lot of work, but is probably more effective than trying to, push a nail in with your hand, right? Still, it's useful. We have functions, right? Functions work pretty well as abstractions. We can have loops to kind of do things multiple times over some data structure. These are great abstractions that we can use. We can have memory, right? We can have pointers into memory. Memory is a fantastic abstraction to use in C++. It allows us to take the lifetime of objects and move them out of lexical scopes and do all kinds of other wonderful things. These are also really fundamental abstractions. Almost every language has them. We know about them really well. We expect every program to use them. These probably aren't the primary problems. Let's talk about C++. C++ brings us an important baseline abstraction level. Your typical work hammer to get things done in C++ is the type, right? Everyone has types. These are great abstractions. We even have more powerful abstractions in C++, really powerful ones. Kind of like a sledgehammer that can, actually do some good work here. We have templates, and templates are really, really cool and really powerful. I love templates. We even have bigger sledgehammers. We have metaprogramming in C++, and it's awesome. You can do amazing things with it. We don't just have metaprogramming. We have two different metaprogramming systems in C++. And you can even sometimes use them together. And so that's really great. These are powerful abstractions. We get a lot done with these. I don't even think these are the most powerful, though. I think that there's an even more powerful abstraction that we tend to use in C++. At least in my code base at Google, we use this very, very often. It's kind of like the largest hammer you could ever imagine. It can do anything, but it's actually not C++ in most cases. It's usually a Python script that generates C++ at build time, and often a lot of C++ and often really complex C++. And of course, this is more powerful than all the others because I can generate all of the other abstractions from my Python script and use them. Okay, so those are abstractions. But what do we mean by cost? What is the cost of an abstraction? And we can break this down into a few areas. The primary cost is going to be runtime, but we also want to think about build time and human time cost. Now, runtime, we understand. If you use too many abstractions, everything slows down, your whole program feels laggy and slow and weird, and it's really frustrating. Almost as frustrating as the DMV. But build time, of course, we typify with compiling, right? We have the best XKCD comment for compiling. But build time is actually a much bigger space than that. Okay, it's not just about compiling. After they fight down the hallway one direction, they come back because they're still linking. And at least in my code base, even after they come back from linking, they still have to load all of the dynamic libraries to run the test, and that's also really slow. So there are a bunch of different things in the build space that add cost to our abstraction mechanisms. And for humans, we also have costs, right? It takes a lot more of your brain to think about and work with complex abstractions. I mean, functions are pretty easy, but when you get to types and templates, much less generated code, it can be incredibly difficult to reason about how your code works with these abstractions, okay? And these are real human costs of abstractions that we need to remember. Now, why aren't these costs zero? Why can't we get rid of these costs? Fundamentally, we're doing work with the abstraction. We're getting some value out of it. It's doing work on our behalf so that we don't have to do it kind of manually and mechanically ourselves. When we do work, much like in physics, energy is required, and you can't make energy just go away. If anyone here has a perpetual motion machine, please let me know. No? Okay. But, energy just moves around. We can transfer it from one place to another, right? But it doesn't go away. It doesn't ever vanish, and the costs of your abstractions don't either. And sometimes they can be really surprising. So I want to try and tell you 3 stories that I have about abstraction costs that were surprising, that we didn't really see coming. And the first of these stories is about a system that is really, really important to me. It's called protocol buffers. How many folks here have ever heard of protocol buffers? Wait, you're clapping? Okay. But lots of people know what protocol buffers are, which is good. It's good that we all know what protocol buffers are. At Google, at least, protocol buffers are kind of very fundamental. We solve everything at Google with protocol buffers. Want to build a storage system? We're going to use protocol buffers inside it. Want to do something? It's always going to be protocol buffers. Unfortunately, they also cause a lot of problems. Anything that becomes that ubiquitous causes a lot of problems. And one of the reasons they cause problems is that they're a code generator, right? They're an incredibly big hammer. In fact, they're about the biggest hammer I know how to find. And so when we use protocol buffers, it's tended to come back and cause us some problems historically. But let's do a quick overview of what protocol buffers actually are and how they work. Okay? Protocol buffers let you define messages, right? We have 2 examples here. You can also put fields into them, like X and name, and you can even embed one message inside another, okay? And this basically lets you have nice descriptive data formats that you can serialize and deserialize, and we build a tremendous amount of our technology on top of these. And because of that nesting relationship, because you often will use one message and put it inside of another, maybe multiple messages, and then those inside of still more, our protocol buffers tend to end up looking like some really high fan-out graph, right? As you kind of nest things together into larger and larger messages, and you build out this complex data representation. Now, I said these are really fundamental at Google, and you may wonder, what are we doing with all of these protocol buffers? Well, we're moving them around. You see, we write servers, and they take protocol buffers in, and then they modify them slightly, and then they move them out into a response, and then they do that again and again. And so at Google, there's a common joke that all we really do is move protocol buffers around. And you can imagine what this looks like, right? You take some subgraph of your tree over here, and you're just going to reparent it into some other part of the tree in order to update a message, in order to build a response from some request. Now, it turns out if that's all you do, it can get really expensive, okay? Because these are all objects, and they're very dynamic objects. There are a large number of heap allocations in here, but we also don't want to have too much fragmentation, so these aren't just tiny objects. They tend to have a little bit of aggregation in them. They tend to be fairly complex. We reuse them whenever it's possible. The requests that come in off of the network are often immutable, and so when we build a response, we might have to copy data into the response. Even if we're trying to move these protocol buffers around, we can end up doing a lot of work. And so we wanted to optimize that. There's a pretty good way of optimizing an allocation-heavy, graph-like data structure when you're doing mutations on it, and that's by using arena-based allocation. So there's a project at Google a number of years back to add arena-based allocation to protocol buffers. We dug into the code that was generated for the protocol buffers, and we found where the moving of protocol buffers around was implemented. Now, unfortunately, protocol buffers predate C++11 at Google. And so all of our moving was actually implemented originally in terms of swap. And if you remember from Titus's talk, or if you watch Titus's talk, he talks about how it's really difficult to refactor higher order abstractions. And in the same ways that it's more difficult to refactor a type than it is a function, it's even more difficult to refactor generated code in some cases. Okay, and so now we have generated types. And so even to this day, we still have swaps as the primary implementation strategy for our moves, because reimagining all of this interface is so difficult. And so we need to come into this and somehow add support for arena-based allocations, and if these swaps end up needing to copy for any reason, having a way of doing that with an arena to save on allocation overhead. And so when we implemented arenas, it ended up adding a whole lot of code, And there are a couple of different reasons why we had to add this much code. The first one is that we can't be certain that all of these protocol buffers have been allocated on an arena. And even worse, we can't be certain that they've been allocated on the same arena. And so when we add arena support, we have to test for all of these different conditions to know if it's safe for us to actually use the arena-based swap implementation. And it turns out those tests are really, really expensive, okay? And so we put them in these inline functions in our generated header files to make sure they could get inlined every single place that they're used. The optimizer can remove this runtime overhead of this abstraction, but it wasn't enough, and so we generated an extra method, the unsafe swap. And then we taught other parts of the code generator to generate direct calls to that to skip these extra checks. And we kept using this code generator abstraction to solve our runtime problems because we wanted this abstraction to be a zero-cost abstraction, right? It makes sense. This is in the critical path of every Google server. All of these movements are incredibly expensive. But by the time we finished it, this is a complex change. Like the change from not having the arenas to having the arenas is a really complex change to the code. We don't want to just like throw a big switch and turn it on everywhere. At Google, we have an enormous code base, hundreds of millions of lines of C++ code. We don't want to change all of our servers in one fell swoop. So we made this opt-in. You add a little flag to your protocol buffer message, and it says, hey, I want to use arenas to allocate my protocol buffers, and you get this extra logic, which is great. This means we have a nice incremental rollout. So sometime in late 2013, teams started rolling this out to all of the most important protocol buffer messages in our code base. And it was really easy to do. They just added this one line of code, so they were able to roll it out pretty quickly, even though it was incremental. But we noticed something as that was going on. We have monitoring for our compile times, and they weren't going in the shape that we wanted. And so the red line at the bottom here is the average compile time for a single file in our distributed build system, in our entire code base. The green line is the 90th percentile, and the blue line at the top is the 99th percentile. And you'll notice in late 2013, these lines start bending upwards much more rapidly. I mean, it wasn't really good before that, but it got a lot worse in late 2013. And as we got into early 2014, the situation became really dire, okay? And to understand how bad this is, you have to think about what a build actually looks like. We build all of our software from source. And so if you're building a large C++ application, you might compile hundreds, thousands, even tens of thousands or hundreds of thousands of source files in a single build. And if the 90th percentile is starting to trend upward in a dangerous way, then you definitely have a large number of compiles in one build that are in the 90th percentile, because you're compiling 100,000 files. In fact, the 99th percentile is also in every single build. Okay, and so despite the fact that we think this is rare, in fact, every single developer at Google was hitting the 99th percentile case somewhere, right? If you want to understand the underlying principles of this, there's a fantastic paper by Jeff Dean and a number of others from Google called Tail at the Tail, I think, which talks about tail latency problems in distributed systems with high fan-out. And compilation is essentially a distributed system with extraordinarily high fan-out. And so this is really, really concerning for us. We dug in and discovered that it was this gradual rollout of this arenas flag that caused this, because when they tested it, they benchmarked the runtime really carefully. And they optimized that, they got that to be as close to 0 as possible. But they never really benchmarked the compile time. And how would they? They only enabled it in 1 or 2 places to run their benchmarks. It wasn't until we enabled it systematically everywhere that it became a problem. But once we did, it became a big problem. Because with that 99th percentile in almost every build, builds were routinely hitting a 15-minute compile timeout. Now, I want to be clear. This is a timeout for compiling a single C++ file. A single C++ file was compiling for 15 minutes on almost every build. So we were in a really awkward position at Google in early 2014. We had to make a choice, it seemed. We either get to keep compiling our code, or we get to improve the performance of our code. And neither of these are really attractive options to have to choose between. We would like the third option of both, please. So that's a problem. We didn't really know what to do about it. We ended up building a bunch of really awful hacks that approximated C++ modules in order to fix this, because modules fix this, right? Has anyone hit bingo yet? Anyways, so modules fix this, right? We hoped that modules would fix this. We actually approximated modules in source to start with. And once we'd approximated modules, we then started working on modules for real, and we've actually deployed C++ modules for all of our protocol buffer compiles at Google, because without them, we couldn't compile, right? Without them, we have this choice, right? But they aren't really fixing it. They're helping, but they aren't fixing it. You see, modules made the problem much less urgent. They removed a large constant factor of the compile time overhead. They helped some of the scaling aspects. It's hard to see in the graphs, but if you go back, this graph is actually quadratic. And that's a bigger problem. And modules help with the quadratic nature of this graph. But they don't make protocol buffers free. They don't remove the abstraction cost. And we needed to actually internalize that every time we're going to enhance something like a code generator used ubiquitously, like the protocol buffer code generator, we have to think about the compile time cost, right? Moving abstractions from runtime to compile time doesn't make them free, doesn't make it zero cost, it just means the cost is paid somewhere else. And so I can't emphasize this enough. Compile and build time are non-zero costs. We have been in a real situation where we had to choose between improving runtime performance or not building our software, okay? This is an important thing to realize. So that's my first story of a surprise abstraction cost. But maybe that's not representative. I picked the most extreme abstraction, right, a code generator, and one that we use ubiquitously. We use this thing everywhere. And that's the thing I picked for my story. So let's pick something simpler. Something that everyone uses, that almost everyone here uses. So how many folks here use unique pointer? A few more hands, right? Like everyone uses unique pointer. So let's talk about that. Maybe this one isn't as bad. So surely, unique pointer has the same runtime cost as a raw pointer, right? Who believes that's the case? I sure did about a year ago. I absolutely did. It doesn't. Let's figure out why. So here is the world's worst unique pointer implementation. Please don't copy this code into actual code. This is just meant to illustrate it. We have a type, a templated type, right? We have a pointer in it. We use the constructor and the destructor. The destructor manages our allocation and our lifetime. We have this nice disabling of copies. It's basically what you would expect. Make sense? We have a unique pointer. And when we put it into a function, it works fine for a local variable. Like this code is fine. We don't have any overhead by using unique pointer here. We get exactly what we would need to write without the unique pointer. But this maybe isn't the most interesting thing. The most useful thing for me with unique pointer is the fact that because it's movable, we can actually put it in API boundaries. I mean, we've had RAII for a lot longer than we've had unique pointer. So we've been able to do this for a lot longer. But putting unique pointer into an interface boundary is a huge improvement. We used to have interfaces that looked like this on the left, where we had this raw pointer and a comment that says, by the way, we take ownership. And then you have to, look at the comments and read them carefully to say, do I still own the memory or do you? Right? It was really, really problematic. And then on the right, we have new code, which is much better, I think. We have unique pointer to say, I'm taking ownership of this memory. And this is the use case I have for unique pointer. And so here's foo, a function that takes ownership of some memory, right? It does some modifications to it, nothing fancy, and then it hands that ownership off to another one. You can imagine that foo is very similar to a factory function that you might actually write in your code, right? That constructs some object. Maybe baz is pretty similar to the constructor of that object, right? This should be an idiomatic usage of unique pointer. And so the question becomes, is this zero overhead? And it isn't. So I just took that code up there and I plugged it, I added some namespace prefixes, and I plugged it into Compiler Explorer, and thank you, Matt Godbolt, for building Compiler Explorer. And I got some lovely assembly out, but the assembly was so long, I had to play with fonts to fit it on my slide. And I know you can't read that. No one can read that. It's ridiculous, okay? So I was surprised at how bad this was. I was shocked. I couldn't believe it was actually this bad. People had been grumbling about unique pointer being expensive. It couldn't have been this bad. And so I looked into it, and if you have really good eyes, you can see at the very bottom, the very last line is the giveaway. It says unwind resume. I was like, oh, it's an exception handling thing. Pause. Unique pointer did something even more awesome for us than giving us ownership on the API boundary. It also fixed a potential bug. Because if bar throws an exception, we leak memory here. Right? There's nothing that cleans up if bar throws an exception. Right? Even if Baz throws an exception before it manages to take ownership, we might have trouble here. We don't know for sure exactly how Baz is implemented. But that's actually a really surprising thing. And so with unique pointer, we get reliable semantics. It's handling all of these exceptions. It's handling them and it's making them reliable for us, which is wonderful. But it actually comes with cost. And maybe my original code without unique pointer was correct. Right? There's no exception that comes there. But I know how we can fix it. We just need to clean up our unique pointer example. Okay, so let's add no except to the unique pointer example. So it's not quite as simple to convert from the raw pointers, but the code's shorter. It's better now, right? It's not as good as I would like, but it is a bit better now. But it's still really surprisingly long. And I thought about this, and I thought about this, and I couldn't figure out why this is the case. And then it occurred to me, it's the case because we keep calling the destructor for temporaries. We have to pass in this unique pointer to Baz by value. We have to build a temporary there, and that's actually adding a bunch of code. Well, okay, I mean, I don't really like it, but I know how we can fix this. Let's add some R-value references to our code. And now we're starting to get to the right ballpark. Now we're approaching the level of complexity that raw pointers had. We're starting to get close to zero cost. But look at what I've had to do on the left. I have no accepts and R-value references and unique pointer. The C++ code required to hit a plausible overhead is really complicated, and that's concerning. But I looked at this, and it still doesn't seem exactly the same. So let's compare them. So I've padded out the instructions, and I've brought back the raw pointer instructions here so that they line up side by side, and we can kind of compare what they look like. Now, there's actually an extra instruction in the raw pointer case, which I found interesting, but it's just moving from one register to another, and the reason is because of the calling convention of bar. It's not all that interesting. But in the unique pointer case, we have something really interesting. We have two extra instructions here. And these aren't trivial instructions. These are loading from memory. And it's worse than loading from memory. These are loading from memory in a critical path. The next instruction after each of these loads from the address that they produce. So we have two loads from memory in a critical path. This is literally twice as slow in terms of latency on your memory subsystem. Okay? This is a very significant cost. Now maybe one of them is in the cache, or more likely to be in the cache. So maybe you get a low memory latency on one of the two, but it's not going to be zero, right? Getting this abstraction to be zero cost is roughly the same as causing memory latency to be zero, which we can't do because of the speed of light. It all comes back to physics. There's no such thing as a zero cost abstraction. Okay, but this is silly. This is because I had R-value references in there. Of course there's two indirections. I put them in the type system. I have a reference to a unique pointer, and then there's a unique pointer. So I expect to have that two-step indirection, right? Right? Okay, so I thought about this some more. Maybe we need to go back to that by value case. Maybe that's the right answer. Maybe that's the right answer. So let's go back to the by value case, but let's zoom in so that we can break down the cost. So this is the bottom of the by value code. Okay, there's some more code at the top, but this is the bottom. And there's some surprising extra costs here that we can try and understand. So there are 4 instructions that come out of this. The first one here is taking some value, and it turns out this is the pointer in question, and we're storing it onto our stack. We're putting it into memory. And then we're computing the address that we just placed our unique pointer in, and putting that into a register called RDI. And the next thing we do is we call baz. So this is putting the unique pointer into memory, then getting its address, and then calling baz with the address of the unique pointer. But I'm passing by value. And it's worse than that, right? We hand baz a pointer to the unique pointer, and then after we call baz, we go back into our stack and load that unique pointer back out of memory, and then we test it to see if somehow baz made that unique pointer not have any memory in it. Well, okay, that part almost makes sense. Okay, that part almost makes sense because we have a parameter, a by-value parameter of unique pointer. And the whole point of having a by-value parameter with a unique pointer is that I'm probably gonna move out of it afterward. But if for some reason I don't move out of it and I return, we have to clean up the memory. And this is cleaning up the memory, okay? This is the destructor for unique pointer. So this is really, really frustrating. We can't actually just pass an object from one function into another, okay? And so we have this, it's still in memory. Even though it's by value, it's still in memory. And we still have a double indirection. In fact, we can see the double indirection if we move back to the top of this function. So this is the top of the by value function. And at the top, you're gonna see those double indirections that we had with the R-value reference. We have the exact same double indirection when we use by value semantics as we do with an R-value reference. Now, here, maybe there's a way to fix this because it isn't in the type system, but it's gonna be hard. So this, like, I really hoped we could fix this, but it's gonna be really hard because we need to do at least two things here. The first thing we have to do is we have to cause a by-value parameter, like unique pointer, to not be passed to a function in memory. We have to move it up out of memory, the way raw pointers are moved up out of memory. But that's an ABI change. That's a change to the calling convention of C++, and a really fundamental one. This isn't like a small ABI change. This will change almost every function call in C++. This is a huge change, and it's really hard to make. And like maybe we can make it smaller. Maybe we only give it for a unique pointer and not for any other objects. But then we have an abstraction in C++ that you can't match by writing C++, right? It's a special abstraction. So this is really concerning. And even when we fix that problem, we still have the problem of an extra temporary because C++ doesn't have destructive move semantics. But if we want destructive move semantics, now that's not an ABI change. That's a much bigger change. That's a fundamental change, the semantics of the language, okay? Now, I don't know about you, but when I realized how much overhead there was here, this was a big surprise to me. I was not expecting unique pointer to come with a runtime overhead bill. And that, I think, is the real danger of zero-cost abstractions, right? And it's completely general. It's not just unique pointer. It's all of our objects and our methods. We assume that they don't come with a tax, but they do. And we have to be aware of that, and we have to think about that when we write code. Otherwise, these abstractions can add up cost on top of cost on top of cost and become a serious problem. Okay, so that's a little depressing. I don't know about you. Let's try something that hopefully goes better. We've gone from code generators down to templates and types. Let's keep going further down the abstraction stack. Maybe we can find an abstraction that doesn't have cost. Surely, extracting a block of code to a helper function is zero cost. How many folks think this is zero cost? It's okay. I know that the narrator says that it isn't, but like, people think this is zero cost? A lot of people think this is zero cost. It should be zero cost. But see, we've talked about build time costs, we've talked about runtime costs, but we haven't talked about the human costs yet. To talk about the human costs, I'm just gonna tell you a story. It's one of my favorite stories. So a long time ago, and I mean like 8, 10 years ago, I was writing some really complicated code. I was a lot younger, I was very naive, and maybe not the nicest person in the world, and I was really proud of my code. I had this really complex algorithm, it had like 3 different phases, it was great. And I'd written it all, it's like 400 lines of code, I had these nice block comments saying like, okay, now we do this tricky thing, we restructure the code into this tricky thing, we do it over here. I was really happy with this code. It was good code. Sent it to code review with my good friend Manuel Klimek. And Manuel Klimek, he works actually on Clang-based tooling and a lot of other things in the C++ community. But he's also, he has a lot more experience than I do. And so when I was kind of young and I sent him this code review, he kind of looked at it, he was just like, oh, kid. And so he came back to me with a really, really pointed code review. And for the record, he was right. And his pointed code review was, this code is impossible to read. You have given me a 400-line function with like multiple phases in a complex algorithm with like 30 different local variables, tons of intermediate state, loops, nested in loops, nested in loops, nested in loops. You have all kinds of things going on here. No. You need to factor this apart. Extract each small piece of functionality into a helper function. Give it a name, right? Break apart your algorithm into phases and separate those into separate functions that you can write your comment on the function instead of just having a comment in the middle of the code, right? Build a type to model the specific data that you're passing into phases of the algorithm and things you expect to get back out. And by and large, he was right. And so I was trying to learn how to do better at writing software, and so I diligently went back and I started refactoring my code. I extracted code into function, extracted code into function, and I got to the end of it and I looked at my code and I couldn't read it. Like I'd written the code. I had no idea what anything did because every time I got to a point in the code, I would have to flip back up pages of code. Oh, what does that function? Oh, it does that. Okay, I go back down and get to the next. Oh gosh, what does that do? Oh, it's that. And then the next one. And this context switching from the top to the bottom, from the top to the bottom, it killed my readability of the code. I just couldn't do it, okay? Now, does that mean that all of this, like extracting functions is bad? No, it doesn't mean extraction functions is bad. It means that it has a cost. It also has a benefit. He was right that my code was unreadable when it started. It was one enormous function. But I probably overdid it when I was trying to follow his advice, and I'd over-factored my code. And that was also unreadable. And you have to get in between these two things, because fundamentally, there's a benefit and a cost to abstractions. And each abstraction you use needs to provide more benefit than cost, right? It's a trade-off. And this is why thinking about zero cost is so problematic. When you imagine you have zero cost, you stop making a trade-off. Everything is better than zero cost. The smallest benefit in the world justifies zero cost. As soon as you make it not zero cost, you can have a trade-off discussion. You can think about what you're giving up by getting your abstraction. So I want to make sure you all have some kind of concrete things that I think you should follow whenever you're trying to use an abstraction and you don't want it to become a problem. You don't want the cost to outstrip the gains. Number one thing, use a simpler abstraction. Don't use a type when a function would do just fine. Don't use a template when a function would do just fine. And please don't use generated code when like a simple function, or even a template, or even metaprogramming would work. Don't go all the way to generated code. And think about where you want to pay the inevitable cost. You will have cost. Where do you want to pay it? Do you want to pay it at runtime or at compile time? Because if you pay it at runtime, maybe that's not a problem in certain parts of your code, and it can make the actual structure of the code much simpler. Then work to reduce the cost as much as possible. Not all abstraction costs are the same, even within a particular dimension, right? You can just use a more efficient abstraction mechanism. And usually, this ties into using a simpler abstraction mechanism. Last but not least, please, 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 please measure that cost. Like, just measure it, and not just in the dimensions where you're expecting to have cost. Because we checked the unique pointer isn't slow to compile, it's very fast to compile, no problem at all. But we never benchmarked the runtime. And so we didn't notice that the assumptions we make about cost and runtime and objects and methods weren't always holding. So it's really important to measure the places where you expect the cost to be zero. And ensure that at the end you've got an actual beneficial trade-off between what you get from the abstraction and what you give up. And I don't want your takeaway from all of this talk to be, gosh, are abstractions bad? Like, are you trying to tell me that I shouldn't use abstractions? Abstractions aren't bad, I promise. That's not the lesson to take away from this. The lesson to take away is that abstractions are like fire, okay? I think about it, fire's a good thing. Fire is the basis of civilization, right? Fire lets us be warm, it lets us cook food, it lets us build things, it's amazing. Fire is fantastic, all right? So are abstractions. Abstractions are the basis of all of our software. Every piece of software we have built is built on top of a stack of abstractions. If you got rid of abstractions, we would not have software engineering. We wouldn't have any software. We wouldn't have our laptops. You wouldn't be able to look at this presentation. You wouldn't have these nicely rendered emoji fire flames. Abstractions are important for software. But fire can also burn, which is not good, right? And abstractions come with costs. As long as we're thinking about the trade-off and we're using abstractions where we need them and we're being careful about the costs incurred, abstractions can be good. They can be really, really good. But they can also go badly when we fail to do that. So fire is good, but also bad. And abstractions are good, but also bad, right? Because there are no zero-cost abstractions. Thank you very much. And we have 2 wonderful microphones. Please, please queue up. I would love to have all of your questions, and I will try to answer them. I don't promise I will succeed.
Okay, great talk. A few things about unique pointer example. The first thing is that you didn't mention inlining at all. I wanted to know if that assembly was what would have been generated with inlining or not, because that matters a lot.
This is a great question. So inlining is why we expected unique pointer to get close to zero cost. And I generated all of those things with O2 optimizations and all of that. All of the actual unique pointer code was gone. I mean, if we can get my slides back up. Like, the only calls here are to things we can't inline. So operator delete isn't inlineable, right? And baz and bar are external functions, right?
Yep.
All of this stuff is not inlineable. So yeah, there's no difference.
Makes sense. One more thing was, in the structure of your implementation, you had a check against null pointer before calling delete.
Okay.
I was under the impression that wasn't required. Is there any reason why that is there?
So you don't think that this check before I call delete is required? Yes, I can just call delete here, but it doesn't materially change anything.
Okay, it doesn't change the assembly.
No, it doesn't change anything.
Cool, thank you.
Not a problem. Yes.
Hey, Chandler. You mentioned the fact that the committee missed something, like maybe there are some assumptions that were made and we forgot to benchmark some stuff. Do you think that there would be a need to a better discipline, or maybe like a reference document or suggestion for every proposal that comes in the language as to what we should actually consider in case something gets missed like that?
This is a great question. So I think I may have overstated things slightly. I'm not trying to say that the committee just like put in unique pointer. They didn't run a single benchmark. I can't believe that's the case. There's no way that's what happened. However, I think that they missed a surprising overhead. At least when I've talked to people on the committee and I've explained the overhead of unique pointer, they were surprised. And certainly I was very surprised when I realized how much it was. And I think what this comes down to is that how you benchmark for overhead is really complicated. So for example, and Vittorio started to touch on this, if all of the code that touches your unique pointer gets inlined away, if all of it goes away, then maybe the compiler gets really lucky and like shoots down every single one of these costs and your micro benchmark is fantastic, right? But in real world code, that doesn't happen, right? And like sometimes it does, but it doesn't always happen. It doesn't reliably happen, and it doesn't happen often enough that it started to come up as people noticed, well, I just added unique pointer to 500 interfaces using like a nice large scale refactoring, and I actually got a measurable slowdown. That's a really hard thing to benchmark for. I'm not sure how best to do it. And so I think the real thing here is that we need to start coming up with how do we benchmark these things. It's not even that we need to remember it. It's that we need to understand what benchmarking we should be doing, and we need to be benchmarking the right things.
Thank you.
So I'm going to get some interesting questions on Thursday after my Back to Basics talk on smart pointers, where I encourage everyone to pass them by value. So thank you for that. I did want to mention, though, at the end of this non-basic talk, that the trivial ABI attribute is supported, at least by Clang on the Itanium ABI. And while it will never get added to standard unique pointer because of ABI, if someone in this audience were like, oh, I have a bunch of int stars that I want to make into std unique pointers, but now I'm scared to do so, you could make your own unique pointer class, tag it trivial ABI, and you would get the identical code gen.
So two things I want to point out. One, I still think you should pass unique pointer by value. Because if I put the R-value reference into the type system, I can never fix this. I at least have a chance when it's by value. So I don't think this changes the guidance. It's just that we have to internalize that there's a surprise waiting for us.
Thank you for saying that explicitly.
Yes. The second thing I wanted to say, though, is I'm not sure the trivial ABI tag is going to work the way we want. I would need to look into it, but I'm really worried that it may interfere with the move-only semantics. And I know that with some smart pointers it doesn't work because they aren't trivial.
Well, I'm not talking about my trivial relocatability, but there is that trivial ABI that changes basically who is responsible for destroying it and would get it passed in a register. This does actually work as far as I know.
Okay.
There was something, but it changes the calling convention in the sense that now it is the callee's responsibility to destroy.
So thank you. Now I'm remembering, thank you for mentioning that. I'm remembering more of this trivial ABI. So it doesn't work, and this reason it doesn't work is super surprising. By moving the responsibility for destroying the unique pointer into the callee, right, the function you're calling, you don't just change the ABI, you change the order of construction and destruction. And the worst thing is, it makes them non-nesting. And so if some of your parameters use this ABI attribute, especially a unique pointer one where the destruction releases memory, and other parameters don't, and they can refer to each other in any way, the misnesting can cause a use after free. And this is actually a problem we've seen in the wild before. The only way you can get close to this working is with what Microsoft's ABI does. And so in Microsoft's ABI, at least some of them, all of your objects are destroyed by the callee. But that's also hard to make work in a conforming way because of temporaries that are destroyed by the caller. And so there are actually conformance problems on Microsoft's platform with that ABI. So
right. This is clearly something that would never go into standard unique pointer, but if someone wrote their own code bases, callee destroy unique pointer, they could get that performance back if they were concerned enough by what you just presented that they were worried about the performance. I would encourage them to try that rather than using raw pointers everywhere.
It's better than using raw pointers. That I agree with.
Thank you very much for nice talk. But the question is, what kind of cost should I expect from tagged integers, so that if I would like to distinguish different kind of integers of the same size?
This is a great question. I have a slide for it. So, I don't know, because I don't know how you implement tagged integers. But I did have some steps that you want to follow. And the notable one is the fourth bullet point. You've got to measure this. The only way to know how much your tagged integer class is going to cost is to measure it. You've got to look at things like the ABI. We just had a long discussion about like a trivial ABI. It's easier to get that with your tagged pointer, but you need to make sure that you got it, right? You need to look at things like what happens when you destroy it. You need to look at how inlineable the methods are. But I want you to understand, it's going to come at a cost. Best case scenario is that you make the compile time pay that cost instead of the runtime. It is not free. There are even ways that tagged integers can create runtime cost that I think is really interesting. So when you have a tagged integer, you have two integers that are functionally the same, but your tag separates the types so that they are distinct types. This gives you nice type checking properties. In C++, one of the consequences of that is that if you build, let's say, a vector of that tagged integer type and a vector of a different tagged integer type, they're two different vectors, and you can't trivially move elements between them. That's what you want, right? The downside is that now you have two different vectors, which is going to require generating twice as much code. And if your application is large enough, having twice as much code may be a real performance problem because of processor limitations. Processors get slower the more instructions that they have to execute. And so by separating all of your templates into two implementations, because you separate the types into two types, even if you make the types fold away, you can still have runtime overhead. Now, in theory, we can go and make our compilers even smarter and more cleverer so that they merge these common definitions back together after they do type checking. But as far as I'm aware, almost no compiler implements this by default. There are experimental options in a few compilers that aren't turned on and that don't have the best results. So I think you may still be surprised, which is why I really encourage you to measure this, not just at a micro level, but actually at a macro level to understand what the costs really are.
Thank you for pointing that part, but compile time cost could be compensated by readability and less error prone. But again, you're right, it is a trade-off.
It's always a trade-off. It's always a trade-off.
Hey, Chandler, thanks again for the great talk. You always give such a great talk. Thank you for bringing up arena memory, which is near and dear to my heart. Thank you for mentioning C++11, where we didn't quite get it perfect and missed it by a little bit. And I wanted you to discuss the difference in the zero overhead abstraction of the C++11 allocator versus the 17 allocator. And do you think it'd be worthwhile if we got everything out of the way? And if you want to see that talk, it's tomorrow, mid-afternoon.
Okay, so want to make sure I'm understanding correctly. You're wanting to think about the distinction between the allocators, which are part of the template type, and kind of force instantiate a specific type for a specific allocator, versus the polymorphic allocators where you have a type erasure and indirection to remove the particular allocator from the type and just have a runtime dispatch.
And in particular, the 11 model is truly as zero overhead as you could possibly have, and the 17 model is zero-ish overhead in spirit, but usable. And we're looking for something that doesn't give up any more, but gets rid of all of the human cost associated with allocators.
So the thing I disagree with is I don't think any of these are zero cost. With C++11, we had a very high human cost, and we had a very high compile time cost. And in many cases, with the allocators in particular, a high build time cost because of having so many template definitions fan out, right? The runtime cost was lower, although it still wasn't quite zero, it was very, very low. There I agree, it's very, very low. With polymorphic allocators, we do reduce the human costs and the compile time costs, but I think you have a very significant runtime overhead. Adding indirection, adding type erasure or virtual dispatch, however you implement it, that indirection on the allocation path, I think is a really expensive thing to add and problematic for a lot of workloads. There's a talk on our memory allocator, which I think actually touches on the degree to which our memory allocation path is performance sensitive.
Okay, and then the third part is we're still in the middle range. We haven't really made it nice for people yet because even C++17 requires a tremendous amount of effort to plumb the allocator throughout the infrastructure.
Yeah.
And the question is, if we didn't lose any more performance at all at runtime, but we made all of the costs go away essentially to zero, so all you had was the goodness of the current allocators, plus that they were completely interoperable with every other language feature, which they aren't today. Would that be a good thing to move towards since we're already here at 17?
So personally, and this is my position, I know that you and others are probably going to disagree with this, but personally, I don't think that the runtime cost of the polymorphic allocators, even setting everything else aside, just the runtime cost is a reasonable overhead, and I don't think that the human or compile time cost for anything that isn't runtime dispatched is reasonable overhead. I just don't think that the allocator model is one that works, but that's my personal opinion.
Okay, and the final thing is we're trying to prove you wrong because we want to put it as part of the language, and I know that's a scary thought, but there's a talk tomorrow that Alistair and Pablo are going to give, and if you're a skeptic, I really hope you come see it. It's the middle one in the afternoon.
Okay, let's get some more questions here.
So I don't want to talk about my talk. I have a more substantial question. I always learn that ABI changes are hard. And one question I have is, you showed a piece of code where the unique pointer was put into memory and then the address of the indirection was passed. Could that actually be changed to just pass it in the register as the plain pointer or not? Is this a fundamental thing on the language semantics, or is it just because?
So this is a great question. And this is actually what Arthur was talking about when he mentioned that we have a trivial ABI tag. So you could imagine creating an ABI that instead of putting this in memory, which we have right here, putting it in memory and then loading it back out of memory after the call, that instead we put it into a register. But one of the tricky parts of doing that is that you're going to have to put it into a register and then pull it back out of a register after the function call in order to keep the sequence of construction and the sequence of destruction nesting in the correct order. And that's a very complex change to the ABI. We could do it, but it's a complex change. And the most interesting thing is it won't be free. So by having it be both an input and an output, it's actually going to cost us something, but we could probably get closer. Because if you think about a raw pointer, the raw pointer we just get to assume isn't coming back out, right? And that assumption reduces the cost because it's not pinning down an output register anymore.
You would have to push it locally within the called function to save the value.
And the ABI that Arthur mentioned does exactly this. And so it pushes it in and it makes the called function handle destruction. But when it does that, we construct things, we destruct some things, then we skip the unique pointer, we keep destroying, right? And the unique pointer is destroyed inside of the called function. And so it unnests the destruction order, which would be a very, I think, difficult change to take in C++.
But to make clear, that's only true for non-trivial types. So any kind of wrapper that I write that doesn't have a destructor, I just can pass it as a register.
Trivial types work a little bit better here, but unique pointer needs a destructor to do its basic work. And that's the challenge. And this is why I think only with destructive move semantics can you really get back to the raw pointer efficiency.
Hey, great talk. I have questions. So can you think of, off the top of your head, any other commonly used abstractions that have unexpected costs that you didn't go over here that we could look up later?
Sure, tuple.
Okay.
If you look at the definition of tuple, you'll understand the compile time cost because it'll take you a while to look at it. Literally, it will take you a while to scroll down and look at all of it.
Anything that's like built into the language and not the library?
Things that are built into the language. Lambdas. Lambdas have some surprising abstraction costs. So when you do a lambda and you have some code inside the lambda body, you may have dead code inside that lambda body, right? It may not be reachable in practice. Maybe it's behind a preprocessor macro or some kind of constant. But if that dead code references any local variables from outside the lambda, they still have to be captured, even though the code is dead, because the ABI decides on the exact capture size and capture list before anything like optimizations are applied. And it's actually part of the ABI, so we can't even change this easily. Both GCC and Clang, for example, which have a compatible ABI implementation, have to somehow agree on the exact same set of captures for every lambda, and that creates a lot of challenges with performance. Vittorio wants to make a comment, but there's this wonderful microphone he can get to in order to make that comment.
They also don't do empty-based optimization. So if you capture a bunch of empty things, like for metaprogramming, or they're going to be a huge lambda object.
Yes, they also don't do empty-based optimizations. We could start doing that now that we have a new feature coming in C++ 20, which is no unique address. Unfortunately, adding functionality for that breaks the ABI, and so it's a backwards incompatible change, and we're stuck with the overhead.
So you mentioned a few questions ago that you had opposition to PMR because of the vtable lookup.
Yes.
If we had some way to conditionally static assert in certain build types that those calls get devirtualized,
yes.
Would you still have that opposition?
I mean, my opposition isn't because there is necessarily one. It's because sometimes there is. We have this ability. We have compiler optimizations that are really good at devirtualization. We have annotations that can help them out. You can profile your code to help them out. But sometimes that's going to fail. And I think that having that kind of indirection that can fail and creates kind of unpredictable performance is a really significant cost around allocation.
Right, but if you could static assert that it wouldn't fail?
It would only help in the places where you can static assert it. You still have the cost everywhere else.
Okay.
You mentioned a couple of times a destructive move. What
Yes.
more detail is that, and how does it help here?
That's a great question. So the idea of destructive move is that you would actually move things into functions in a way. The lifetime would be transferred in as opposed to having these objects that are moved out of come back and still have to be destroyed. And if we had something like that, it would be a lot easier to express the semantics that Peter and Arthur are talking about, where this object doesn't come back and get destroyed in the kind of nesting structure, but its lifetime is actually transitioned into the function I'm calling and taken over by that function and managed inside that function. It is, I think, the right mental model with which we can move away from a strict nested lifetime system. And there are some advantages to that around efficiency. It helps with some overhead. There are also disadvantages. I don't want to give the idea that this is a clear and trivial win. Nested lifetimes is a much simpler model. Having destructive moves and allowing to escape that nesting creates some amount of complexity. The question is it worth it?
Just so I'm clear, the destructive move idea would then only apply to function calls rather than any random place you use move now.
We don't know what it would look like, but we could investigate that if we decide that this kind of problem is one we really need to fix.
Thank you.
Along those lines, isn't this test instruction an optimizer bug because the user has dereferenced the pointer, making it undefined behavior for the pointer to be null? And if the user, the semantics of move on unique pointer are well defined in the standard, so the compiler should not have to do that test, correct?
The previous call could have made it null.
No, because it's being dereferenced inside of foo. And so
Yes, but Baz
UV
could
to
have made it null.
dereference
No, but Baz could have made it null. In fact, in most cases, we expect the test to always fail. It's always null coming out. That's the common idiom, is that you pass the object into Baz, Baz takes ownership and moves it somewhere else. And we just leave a null pointer around to come back out and skip the call to delete. Now what we could do is we could fold the test into the call to delete, but I don't think that really saves us a whole lot.
Okay.
Hello. So I think as many people here, I was surprised by this actual code which is generated for a unique pointer. So I tried actually something with a simple structure where I just put a pointer because I said, okay, unique pointer is a pointer and a deleter. And so in this case, if you just do that, structure coercing works and you actually have stuff by registers and by value as you would expect. So my question is, what exactly is done is unique pointer which makes this not possible? Why structure coercing doesn't work in this case? So if we take, this, so the only thing that miss here from the real unique pointer is the deleter, all right?
So if you look at this destructor, it's accessing raw putter. And I had a slide, sorry, I had a slide to try and talk about this and I deleted it. I clearly should have kept that slide. So if you look at this raw pointer, that's not just accessing raw pointer. There's this implicit this that's a pointer to the object and an arrow, and then raw pointer.
Yeah.
That's where the pointer comes from. Does that make sense?
Yeah, but if you do this and you pass this structure by value, you actually will have structure coercing within the ABI or this stuff, and so you will have really the raw pointer value passed by register. I mean, if you try it works. So my question is what exactly the unique pointer is done which makes so that it doesn't work?
So the challenge is that if you want to pass it by value, you have to pass it back out by value because the destruction happens after the call completes, right? And so we choose in our ABI, and maybe this is the wrong choice, but we choose in our ABI to instead put it in memory so that we can call it, and then after the call completes, we can run the destructor on the same object.
Okay, yeah.
And even then, being able to do this would require us to do some analysis here that we might not succeed at. Because we don't just have to prove that we could pass it by value. We have to prove that the address of the object isn't captured by this object in some way and observed. And maybe with unique pointer we can do that. Probably with unique pointer we can do that, but it still ends up being a more complex trade-off. And it would be a new ABI, and taking the ABI break is the problem. We probably could, in theory, fix this. I think we can fix this. But doing so is going to require at least an ABI break. And that's the challenge. That's the real challenge here.
Okay, thanks.
Okay, last question, and then we gotta cut this off. Go ahead, Marshall.
I just have a comment. I'm pretty sure you can't do that in the existence of user-supplied destructors here.
The question is, you can't do it in the presence of user-supplied destructors.
You can't prove that when the user supplies the code to do the destruction, because unique pointer doesn't have it does have a deleter.
Yeah, it has a deleter. I just skipped it to
I'm
fit.
just saying, if you have a deleter that's supplied by somebody else that may be opaque to you or may be transparent, I don't think you can prove that.
Yeah, in the place of a custom deleter or anything else that makes this code opaque in some way, then we're out of luck. Again, ABI break is just the first step necessary to fix this. It's gonna be hard. That's why I'm not sure we're gonna succeed. All right, thank you everybody. It's been a lot of fun.